Now we will look at the third and final case, in which we don't have a finite number of points, but an infinite number of points. So in this situation, rather than thinking about individual point masses, we will think about a lamina, which is a thin plate that occupies a region R of the plane. So you can think of this as a strangely shaped plate. It's flat, and at each point there is a mass. For the purposes of this class, we will assume that the lamina has uniform density rho. So rho is just a number indicating how heavy that plate is or how dense that plate is. Language, the center of mass of a lamina of uniform density is also called its centroid. So our overall question is, okay, I have this lamina. Say I want to balance it somewhere. Where would I have to put a little stick under it to make it balance? Right, and so it's generally somewhere toward the middle is our understanding, right? We can't put a stick under our lamina right here and have it balance, right? It's going to tip over. So for our setup, we are going to suppose that our lamina lies below some curve that we'll call f of x and above a second curve that we call g of x. And it's between x value a and x value b. We can find the mass of the lamina just by taking the area and multiplying by that density rho. So rho times its area, but we know that the area between those two curves is the integral from a to b of the top curve, f of x, minus the bottom curve, g of x, integrated with respect to x. To understand this, we'll take the interval from a to b and subdivide it into n equal subintervals, each of width delta x. Then we will label the endpoints of those subintervals, x0, x1, all the way up through xn. These subintervals then divide our lamina into strips of equal width. If we focus on the ith strip, so from xi minus 1 up to xi, and we call xi bar the midpoint of that subinterval, then we can use that midpoint to approximate the top and bottom of that strip and approximate that strip by a rectangle whose height is given by f of xi bar, the top y value, minus g of xi bar, the bottom y value, and width delta x. Okay, so let's just focus on that ith rectangle. For this rectangle, we can find the mass by taking the density times the area. Well, the area is length times height, or width times height, and the width we know is delta x, and the height is f of xi bar minus g of xi bar. So the mass is rho, the density, times the height, f of xi bar minus g of xi bar, times the width, delta x. To find the center of mass, we just need to find the geometric center of the rectangle. That's because the density is constant. So we can easily see that the x value of that center is xi bar. To find the y value, we need to find the height of that rectangle, which is f of xi bar minus g of xi bar, and divide by 2 to find half of the height. And then we need to add that bottom y value. So we take g of xi bar and we add half the height of the rectangle. Then by the time you get a common denominator and combine these terms, you end up with 1/2 f of xi bar plus g of xi bar. Okay, if you're not quite seeing that, just take this guy and multiply by 2 over 2 and add the fractions. So that gives us the y value of the center of mass of that rectangle. In order to find the moments for this one rectangle, we remember that the moment about the y-axis is the distance of our point mass from the y-axis multiplied by the mass of that point. Well, thinking about this rectangle as being a point mass centered at this midpoint, this middle point, the mass is rho times the area of the rectangle. The area of the rectangle, we said, is f of xi bar minus g of xi bar times delta x. And the x value of this point is xi bar. So the moment about the y-axis, just changing the order of those factors, is rho xi bar times the quantity f of xi bar minus g of xi bar times delta x. For the moment about the y-axis, we take the y-coordinate of this point and multiply by the total mass. So we take the mass and multiply by the y value of that center point. Well, the mass again is rho times f of xi bar minus g of xi bar delta x. Okay, and the y value of this point is 1/2 f of xi bar plus g of xi bar. Putting this together, we have a factor of rho and a factor of 1/2 that we can write as rho divided by 2. Then we have f of xi bar minus g of xi bar, f of xi bar plus g of xi bar, and then a factor of delta x. Now take those two, FOIL them, and you end up with this f of xi bar squared minus g of xi bar squared. Okay, so these are the moments we just figured out. Then we do this for each of those rectangles. We take the moment about the y-axis for each rectangle, which is this expression. We add that together for each of these individual rectangles to get the moment about the y-axis of all of the rectangles put together. We do the same thing for the moment about the x-axis. And then to get to the moment of the lamina, which is approximated by those rectangles, we do our usual thing and we just say, well, take more and more rectangles. Take the limit as n goes to infinity of the moments of the rectangles all put together. We recognize this as the limit of a Riemann sum. And so the moment about the y-axis is the density rho multiplied by the integral from a to b of x times the quantity f of x minus g of x integrated with respect to x. And the moment about the x-axis is the density divided by 2 multiplied by the integral from a to b of f of x squared minus g of x squared integrated with respect to x. Now, putting that together, we find the centroid of the lamina. It is an ordered pair x bar, y bar. And x bar is the moment about the y-axis divided by the mass. Well, the moment about the y-axis is rho times the integral from a to b of x times the quantity f of x minus g of x dx. And the mass is rho times the integral from a to b f of x minus g of x dx. We observe that the density rho cancels, so we have the integral from a to b of x times f of x minus g of x dx divided by the integral from a to b of f of x minus g of x dx, which is the area of the lamina. To write this more succinctly, we take 1 divided by the area, and we multiply by the integral of x times the top function minus the bottom function integrated with respect to x. Similarly, the y value is the moment about the x-axis divided by the total mass. The moment about the x-axis is rho divided by 2 times the integral from a to b of f of x quantity squared minus g of x quantity squared dx. Again, the mass is rho times the integral from a to b f of x minus g of x dx. The rows cancel, and so we end up with 1 divided by 2 times the area. So the 2 is this one, and the area is this integral in the denominator, multiplied by the integral from a to b of f of x quantity squared minus g of x quantity squared, integrated with respect to x. Now let's look at an example. So we will find the centroid of the region bounded by the curves y equals x to the third, x equals 0, and y equals 8. First, just to get an understanding, let's sketch these curves. So y equals x to the third looks roughly like this. X equals 0 is the y-axis, and y equals 8 is a horizontal line. So the region we're looking at is this. We would expect the centroid to be a little bit left of the center here and a little bit above the horizontal center. So I would estimate right about there. Let's start by finding the area, because this is more familiar to us. So to find the area, we need to integrate from left to right. So the left x value is 0. This x value we can easily figure out is 2, integrating from 0 to 2. The top curve is y equals 8. The bottom curve is y equals x to the third, and we integrate with respect to x. Our antiderivative is 8x minus 1/4 x to the fourth. We evaluate at 0 and 2, getting 16 minus 4, or 12. To find the x-coordinate of the centroid, we take 1 divided by the area, and we integrate from 0 to 2, a to b, x times 8 minus x to the third dx. I just want to point out that this integral is nearly the same as the integral we used for area, just with an extra factor of x. I'm telling you that only to try to help you remember. To integrate this, we need to first distribute that x. So we integrate 8x minus x to the fourth with respect to x. Then our antiderivative is 4x squared minus 1/5 x to the fifth. We evaluate at 0 and 2. We get 1/12 times 16 minus 32 over 5. When we plug in 0, we get 0. And this gives us 4/5 overall. To find the y-coordinate of the centroid, we remember our formula. We take 1 divided by 2 times the area, which is 12. We integrate from a to b, or 0 to 2 in this case. And at this point, our integrand is the top function squared minus the bottom function squared. So we have 1 over 24 times the integral from 0 to 2 of 64 minus x to the 6 dx, or 1 over 24. Our antiderivative is 64x minus 1/7 x to the 7th, evaluated at 0 and 2. So 1 over 24 times 128 minus 128 over 7, and that boils down to 32/7. So our centroid is x bar comma y bar, which is 4/5 comma 32/7. Just for understanding, 4/5 here is a little bit less than the x value 1. and 32/7 would be the same as 4 and 4/7. So on the y-axis, we're a little bit past 4.5. So around here. And so our centroid is this point. So my estimate a little bit ago was a bit off, but still within the realm of believable. Okay, and then as a reminder, if I took this plate, this lamina, and I centered it on a stick or on my finger right here at this point, it would balance, it would not tip.